posted on Facebook with his picture right next to the picture of Zach Galifianakis saying, "It's not a purse, it's a satchel." Indiana Jones had one. Funniest picture ever. Oh my gosh. It's hilarious. Emily was like, oh my gosh, it's so great.
What is this?
And on Instagram, we took a
It's
picture
like
of
that
it.
proud moment where it's like, I'm so happy, it's like my brother.
It's on Instagram, we took a picture of my friend with the dress Jackie Chan. They look so solid.
Ew.
What?
A red Cheerio?
I don't know what it is.
I cheered.
I had some weird cereal, but it was very good.
Excuse me. Okay, so when we went through things yesterday, we got talking about the law of cosines, and we derived a formula, a little bit bulky to be sure, but it is useful to solve triangles that law of sines can't. I just want to make a comment before we move on. The cosine of a 90-degree angle, is, calculator over here. 90 cosine. I guess I didn't even need the calculator, so I'm thinking it, because, yep. All points in the unit circle are in the form cosine comma sine. So cosine 90 is 0. Think about this for a second. What if you had a triangle where angle C was a right angle? Side C is over here. Here's angle B and angle A. Side A and side B. If you used this form of the law of cosines, C squared equals A squared plus B squared minus 2AB times cosine C. Cosine C is cosine of 90, which is 0. And 0 times 2AB is 0. And you end up with that. Right? So you could think of a law of cosines as Pythagoras for triangles that don't have 90-degree angles. You could think of it that way. And if your triangle did have a 90-degree angle, the last part would go to 0. Right? So this is a generalization, in a sense, of the Pythagorean theorem. That's good. That's good. Think of Pythagoras as a specific case. Think of law of cosines as a more general case. Because remember, law of cosines can deal with any triangle, any angles, A, B, and C, and any sides, A, B, and C. No restrictions. Right angles, not right angles, acute angles, obtuse angles. Anything is fair play. Now the last example that we did not get a chance to finish, and I want to go through that here, is a triangle with sides, or rather angles of x, y, and z, and sides of 5, 7, and 8. And we're asked to solve the triangle. Anytime you solve the triangle, you will have been given 3 pieces of information. You will be expected to produce the other 3. Now, as a first order of business, try the law of sines. I say this because if law of sines works for your triangle, it's going to save you time, and then you're going to be able to avoid law of cosines completely. So, take a look at law of sines. You would have sine of x over 7 equals sine of y over 8. equals sine of z over 5. Is this about as far as we got?
We did the equation for the cosine.
Okay, so think about this. If you use any of these two expressions to make an equation, you're always going to have two unknowns and basically have no way to solve for the unknown because you have one equation, two unknowns. There's no way to get there. So law of sines is not going to initially work. We step up to law of cosines. What was the letter that I put? I used 8. So here's the idea. 8 squared equals, that's one of the sides squared, equals the sum of the squares of the other sides minus 2 times the measure of each of those sides times the cosine of the angle opposite the side of 8, which is cosine of y. Now, if we simplify this down, 8 squared is 64, 7 squared is 49, 5 squared is 25, 2 times 7 times 5 is 14 times 5, which is 70, or 7 times 10, times cosine y. There's only one variable to solve for, that's cosine y. So we take 64 minus 49 minus 25, and that's going to give us negative 10 equals negative 70 cosine y. We're going to divide away the negative 70 and get cosine y equals negative 10 divided by negative 70 is 0.143. How do we get y? We do the inverse cosine, 0.143. What was that? Question? Confused?
I got to where it's 64 equals 49 plus 25 minus 70.
Mm-hmm.
But how did you get to the number?
Think of this as your variable. So if you're gonna, you ultimately have to get rid of the 70. And to get rid of the 70, you're gonna have to divide. To divide, you're gonna have to do all the addition first. So subtract the 49, subtract the 25. And this is what you're left with. Then divide away the 70. Or better yet, the negative 70.
Oh, so that's what you're being doing there. Okay.
That's why I did it wrong the whole day.
Does that make sense now?
Uh-huh.
Good. So y is 81.8. Now, nice thing about law of cosines is there is no chance of there being an angle in your triangle of 270 to 360 degrees. So, if you have a cosine that's positive, you're guaranteed to be in the first quadrant. If you have a cosine that's negative, you're guaranteed to be in the second quadrant and have an obtuse angle. So we end up with 81.8 degrees, and that tells us what y is. And now, with that information, we can start using law of sines. We made a mistake last time by using the biggest angle with law of sines. Because when we use the biggest angle, there's a chance it's obtuse. So my recommendation here with the law of sines now is to grab a medium or the medium or the small angle. And fortunately, when you look at the side measures here, you are only dealing with the medium or the small. I'll deal with the small just for the sake of try to go after the smallest angle, that way there's no chance it's obtuse. And when you do this, you'll have sine 81.8 degrees over 8 equals sine z over 5. You can cross multiply there. I guess I'll first take the sine of 81.8. That's 0.989 multiplied by 5. We'll get 4.95 equals 8 times the sine of z. We'll divide both sides by 8, and we'll have the sine of z equals 0.619. Thus, inverse sine, z is 38.2 degrees. I suppose, just for the sake of showing this, because sine and the positive value could be an acute angle, or could be an obtuse angle, I'm going to take 180 minus 38.2, to show that the angle could be 141.8. But as soon as you think that side z, or rather angle z, opposite the smallest side is 141 degrees, you would be thinking incorrectly. Because the smallest side of a triangle has to be acute. You have no choice. So the z here is 38.2, and then we sum to 180. We take 180 minus 38.2 minus 81.8, and the remainder is 60. Here we are, and we have solved the triangle. So, anytime you're solving the triangle, first try law of sines. If law of sines works, good, simple. If law of sines doesn't work, you've got to use law of cosine. And after you use law of cosines once, which law of cosines is nice because you will obviously have an angle, the angle is forced. Then come back and use law of sines. My recommendation when you come back to do law of sines is to use the smallest angle available, which ensures that the angle is acute. I think that would be a good strategy, because last time when we did the biggest angle, it was possible that it was acute, possible that it was obtuse, and it made for a harder analysis. Questions on that? Okay. Now, let's jump into section 82. All the logarithm work we've done all year has been leading up to this point. So this will be a satisfying discussion, in a sense, to feel like all that logarithm work was for a good end.
Mr. Bob,
Mhm.
what do we do if we have a negative log?
What if you have a negative log? Like, where x is negative?
The one in the homework said like negative log something raised to something. I wasn't sure what to do with that.
Negative, this was the problem? Yeah, we'll get to the homework in a minute, actually, now that I think about that, because we're out of rhythm. Oh shoot. Here's the way to think about that. This is negative 1 times that, which would be log 1/2 of 4 to the negative 1 power, which when you have the negative power, that means you can put the positive power in the denominator. Is that familiar? And then you have log 1/2 of 1/4, which I believe is 2. Because 1/2 squared is 1/4. Right? So that would explain that. And actually that question is a good one, because remember, one of the rules with logarithms is if you have a number in front, you can bring it up as a power. And if you have a power on top, you can bring it down in front. Remember that, because that's going to come into play. So, let me go here, 82. Exponential equations. Exponential equations. Now, you know what an equation is. That's a statement with an equal sign. An exponential equation is when the variable is in an exponent. We, to this point in our life, have never seen an equation where the variable is in the exponent. I suppose if we ever have seen one, it would have been a basic pre-algebra example like that. This is an exponential equation, and as you can see here, x would be 3. But now what about this? What if we have 10 raised to the negative 2x plus 2 power equals 8? That is one that is less known off the top of your head. right? You know that 2 times itself 3 times is 8, but I don't think you know how many times you have to multiply 10 by itself to make 8. Is that right? Yes? That's a harder problem. Now we got to think about what can we do when faced with an equation. When faced with an equation, we can always do what we always have done, which is do anything to both sides, so long as you do the same thing to both sides, and you're still going to get an equal statement as a result. But one of the challenges in this problem is that the power is up here, the variable is in the power, and we wish the variable wasn't in the power. Well, one thing that we could do to cancel that out would be to take the log of both sides. And when I say take the log of both sides, we can just take the standard logarithm of base 10. We can take a base 10 logarithm of both sides. That's the one that's by default in your calculator, that's just log. Now, what's going to happen on the left? The power gets dropped down, and you get negative 2x plus 2 times log of 10 equals log of 8. Now, we want to solve for the x, so we could divide away the log 10 and get negative 2x plus 2 equals log 8 over log 10. Now, that log 8 over log 10 is something that your calculator can compute for you, because your calculator has a log button, and if you do log 8 divided by log 10, you're going to get something. You'll get negative 2x plus 2 equals 0.903. But 0.903 is just log 8 divided by log 10. And at this point it's really simple, right? Subtract 2 from both sides. You get negative 2x equals negative 1.097. And then you divide both sides by negative 2. And you get x equals 0.548. If you're within a couple decimal places of that, that's fine. Now, what does that mean? That means if you plug this value in for x in the original equation, the equation would be true. Let me prove to you that that's the case. If I go into the original equation and do negative 2x plus 2 when x equals 0.548, this is just a check I'm going to do over here. You're going to get 2 times 0.548, that's negative 2 times 0.548, plus 2 gives you 0.904. And that was the power that was on the 10. And if I take 10 and raise it to the 0.904 power, I get 8. How cool is that? Maybe not so cool by your standard, but the big idea here is when we've had equations, we've added something to both sides, we've subtracted something from both sides, we've multiplied something to both sides, divided something to both sides, we've taken square roots of both sides, we've squared both sides. I don't think we ever have taken the log of both sides. But it's a valid thing to do because you're doing the same thing to both sides. And the advantage when your variable is in the exponent is taking the log of both sides brings the power down, puts the power in a position to where it can be more easily worked with. So that's the reason why, the big reason why we got comfortable with logs, really, when it comes down to it, is to be able to solve exponential equations. To be able to solve equations that, if you didn't have log, there would be no way for you to figure out what that power is very easily. There wouldn't be a way. Excuse me. Okay, so let me do another one. Solve. E to the negative 2x plus 3 equals 5. I'm going to prove a point with this problem. First, I'm going to solve it the good old-fashioned way, then I'm going to solve it a slightly different way. You'll see that it'll work both ways just as well. So notice the variable is in the power. So what do you want to do? You want to get the power, you want to get the variable down out of the power. How do you do that? You take the log of both sides. So we'll take log of e to the negative 2x plus 3 equals log of 5. I'm not writing the base in here because the base is just the standard logarithm, common logarithm of base 10. Now, when you have a power, you can bring the power down. Negative 2x plus 3 times log of e equals log of 5. If you divide away log of e, you'll get negative 2x plus 3 equals log 5 over log e. And you can do this on your calculator as well. Now, to know what e is, there's two ways to do that. One is you can remember that e is 2.71818. That's one way to do it. You could just remember that and plug it in, just like you could plug in 3.14 for pi. That's a possibility. Another thing you can do is there's a button on your calculator, e raised to. You could raise e to the 1 power, and that will give you 2.71818 as well. So if you do the e to the power, oops, 2.71828. So one way is to just remember it, the other way is to use that e to the 1, and then that's going to give you what e is. But what you need to do is take the log of 5 and divide it by the log of e. And when you do, excuse me, you'll get 1.609. Yes? Is that what you guys got?
No.
So what I typed into my calculator was log 5 over log e, which is really log 5 over 2.71828. Log 5, 0.6989. 2.71828 log is 0.4343, and then you divide, and 1.609.
I keep it 1.06.
1.06?
Yeah.
Did anybody else get 1.06? At this point, subtract 3 from both sides. Did you get it right?
Yep.
Good. 1.609 minus 3, that's negative 1.391, divide by negative 2, and you get x equals 0.695. You can be off by a couple decimal places, that's okay. Now, I wanted to prove a point with this problem, and I'm going to now. The point being that notice how we took the log of both sides, which is legal, that's doing the same thing to both sides, and that's not going to change whether the equation is true or false, it's just going to express it in a different way. But in this problem that has an e involved with it, you could take the ln of both sides. So if you took the ln of both sides, you get the ln of e to the negative 2x plus 3 over the ln of 5. When you drop the power down, you'd have negative 2x plus 3 times ln e equals ln 5. But ln e is something that is easy to determine, because remember, what the base on the ln is e. So you're asking the question, what power do you have to raise e to make e? that would be 1. And anything times 1 is just itself. And if you take the ln of 5, it should give you that same 1.609 number. Kind of cool. So, in some senses it's totally different, because on one hand we were doing log 5 over log e, and that was this complicated calculator entry. On the other side we were just taking ln 5, but it's the exact same value, which is kind of neat to think about. So whether you take the log of both sides or whether you take the ln of both sides, you're allowed to do either, because in each case you're just doing the same thing to both sides.
Oh, because for the e problem we did like the log. Couldn't you do like the opposite, like the ln for like a log problem?
On the first problem we did logs, we could just as easily have done ln's. Is that your question?
Yep.
Yep. So you can do either, basically, because either log base 10 or base e is going to drop the power down. And when you drop the power down, the problem becomes doable. What about this guy? 5 to the 2x minus 1 equals 6, the x minus 2. Take the log of both sides. It's going to bring the power down. Now, in this case, we've got logs on both sides. We've got letters on both sides. It might just be easiest to say, okay, what's log 5? Use your calculator. 0.698. And what's log 6? 0.778. And then take those numbers and distribute them. So 0.698 times 2 is going to give you 1.396x minus 0.698. Just distributing the 0.698 to the two terms, and then distribute the 0.778, you'll get 0.778x equals, or rather minus 2 times 0.778 is 1.556. Problems like this are really common in biological situations when you have bacterial growth, so it's good to get comfortable with these big decimal equations, because what you need to do is subtract 0.778x from both sides. I'll show all the steps just so that you can see it. So when we take away 0.778x's, we're left with 0.618x's minus 0.698 equals negative 1.556, and then we have to add 0.698 to both sides, and we get 0.618x equals 1.556 in the negatives plus 0.698 is negative 0.858, and then we're going to divide both sides by 0.618, and we're going to get x equal to negative 1.388. So it gets decimal heavy, but ultimately once you get the decimals in there, it's just an algebra 1 problem with large coefficients, bulky coefficients maybe is the better word. So tomorrow we'll go over both homework assignments from yesterday and today. 82 is the section that tonight's problems will come from. 7 through 10. 17. 21. 23. 24. And 27. To bigger and better things and that stuff. Start with homework though.
Thank you.
Bye.